me give you some motivation. Why do you even want to learn about these inverse trig functions? Well, because you learned a little bit about it in a trig class when you took like pre-calc, but they didn't give you everything to know. So let me just do a little quickie review from pre-calc or trig. In a trig class, you probably saw something like, hey, kiddies, sine of theta is square root of 2 over 2. Find theta. And in your trig class or pre-calc, Math 244, Math 104, they probably said, oh, this is not a problem. You're just going to take sine inverse of both sides of the equation. Does this look familiar?
Yep.
Yes.
Yeah.
Yes.
And then on the left-hand side, using your knowledge of inverse functions, when you take an inverse of something, you know, like the square root of x squared would just give you x, right? Arc sine of theta just boils down to what?
Theta.
Theta.
Thank you. And then you go use your graphing calculator or whatever, and you figure out what arc sine of square root of 2 over 2 is. And if you don't remember what this is, it's the, I like to rewrite it in English, it's the angle whose sine value is square root of 2 over 2. And so if you bought your course reader already, give me a shout out if you got your course reader yet. I'm listening. Say woohoo. Well, I heard 4 woohoos. Is that it? There's only 4 woohoos in the whole class? What the hell is wrong with you people? Where the heck is this? Oh, on the very last page of this particular section, you're going to see this unit circle diagram. You're welcome. So on this unit circle diagram, do you see any angles whose sine value is square root of 2 over 2? And I claim 45 degrees or pi fourths, there's the sine value, but there's more than one, right? Like what about over here? What about 3 pi fourths? Which one is correct? Is it pi fourths, or should the answer for theta be 3 pi fourths? Or does it even matter?
I think it would be both.
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 And the answer is there's only one answer. And maybe in your pre-calc class, they allowed you to give 2 answers. And I'm going to tell you right now, you're wrong. Because the function, the arc sine function, has a very limited range. The range is only angles between negative pi halves and positive pi halves. So the only single correct answer is pi fourths. I know there's 2 different angles whose sine value is square root of 2 over 2. I got it from the diagram. But if we're going across in alliance or with the function arc sine, which you haven't learned about yet, you have to honor it. So what's the whole point of me giving you this silly example? Even though in your trig class you may have discussed arc sine or arc cos or arc tan or whatever, all those inverse trig functions, you didn't really learn all the details about them. And I mean massive detail. Welcome. You're going to do that right now. Okay? So let's do a little bit of looking at the sine function, and then we'll be able to, from the sine function, get the sine inverse. So hopefully you guys remember the sine function is really easy to graph. It's a wave. Boy, that looks pretty bad. Well, it's supposed to have some symmetry anyway. And it's got a period of 2 pi. And, you know, the highest it gets is what? What's the amplitude? What's the highest the sine function gets?
1.
1.
Very good. And how low does it go?
Negative 1.
You guys are good. Congratulations. That's awesome. So do you remember when you studied inverse functions, and you probably even did it in a beginning algebra class, that it had to be 1 to 1? In other words, it had to pass a horizontal line test before it could even have an inverse. Just as a side note, do you remember like y equals x squared does not pass the horizontal line test, so it's not 1 to 1, so no inverse exists? I can't write too well. Do you guys remember any of these facts at all from inverse functions?
Yeah, I do.
Yeah.
Okay, good, because you need that now. So what I'm saying is if I perform the horizontal line test on y equals sine of x, check it out. Do you see that I intersect a lot more than once? It fails the horizontal line test. and therefore it is not one-to-one, and therefore it does not have an inverse. Well, wait a minute, what about arc sine? I'm getting there, but this is how they derive it. And you got to pay attention if you really want to think hardcore mathematically. Yeah, I got a lot of math majors in the class. If you want to be a math major, these are the details that you care about, like nobody's business. So back to y equals x squared. Well, I think that there is an inverse. It's square root of x. But here's how they said the inverse could be existing. They forced y equals x squared to pass the horizontal line test. Well, how? They chopped it up. They erased half of it. They said, you know what? We're only going to take, for the right, only one half. Let's take the one, where x is greater than or equal to 0. Now, when you perform the horizontal line test, and by cut out my internet really crappy this morning, I have to rejoin Zoom. Don't leave. Sorry. My internet connection. Oh my God. Please God, do not drop out of the Zoom call. Ugh. Sorry. I got problems. Now it passes the horizontal line test, and now it is one-to-one, and now you can go get the inverse function using your knowledge of finding inverses. And it turns out that f inverse is going to be square root of x. So the inverse can only exist and you have it be one-to-one. So what we do to the sine function, people, is we're going to erase a bunch of it, because it, you know, keeping the entire wave, it ain't passing no horizontal line test. Yes, part of the sine function we keep, we're only going to keep the part negative pi halves and positive pi halves. Okay, well, how come? Because if we keep only that portion like that, now it passes the horizontal line. So it only intersects a horizontal line one time, and an inverse exists. Yay, success. So now you can do y equals arc sine of x. So you have to restrict the domain. So the domain has to be restricted between negative pi halves and positive pi halves in order for this to exist. So then the range. Well, the range is still the same as it was before with the regular sine function. It still goes as high as -1 and as low as -1. So the range is like so. All right, now let's take a look at the graph of y equals arc sine of x. This graph, and I'm not going to ask you to memorize this graph, so don't get too like weirded out. There's only one graph I do care about. That's the arctan. Arc sine, I never memorize it. It looks like that. Well, that's pretty crappy looking, but you get the idea. So the domain is -1 to 1, and notice the domain and the range of inverse functions are always swapped. And then the range is the same as the domain of sine, negative plus to positive pi halves. And that's what I was talking about, why there was only one answer when we're solving this little trig problem. That technically the only true answer is pi fourths because of this restricted range here for arc sine. So real quickly, for arc cos, if you look at the cosine normal graph, ain't 1 to 1 because it passed no stinking horizontal line test. So what are you going to do? You're going to restrict the domain so that, and which part of the cosine will we pick? We're only going to pick the part that goes between 0 and pi. And the range will still be between -1 and +1. Okay? Now it's cool, and now an inverse exists, and that would be arc cos. So what about the arc cos graph? And his.
We can't see Miss Rescue.
Say again?
We can't see the screen of cosine.
Is the screen just.
It froze up. You can only see
froze
the
up.
top half.
Okay, hang on a minute. Let me try to do another share screen. This might be my internet dying. Got it. How about now? No?
Yes, we can see it now.
Okay.
Well,
Let me
kind of.
It looks glitchy, actually.
Yeah.
Yeah, it looks really crappy,
Yeah,
doesn't
not
it?
yet.
Okay. Let me, okay, hold on a second. Yeah. Let's go over here. Let's talk about where your Zoom links are. Hey, did you know that I posted your Zoom links for Monday's recording already? If you go to week 1 and look under Zoom links for week 1, there's Monday's Zoom link recording, okay? Can you guys all see that?
Yeah.
Yeah.
You got to talk back to me because my internet's shaky, and if I don't hear anything, I feel like, oh no, my internet dropped out. So let's communicate.
Okay.
Thank you.
For sure.
This looks still pretty glitchy.
Yeah, I have a quick question about you know how in the domain for sine x you put the same domain and range for arcsine, and I was just wondering like if it was a mistake or
It should be the reverse. I should have done the reverse. Did I not do the reverse? Oh,
I don't know. It was kind of glitchy, so I couldn't really read it.
okay. All right. Hang on a minute. I'm having some serious software problems right now. Sorry.
That's all right.
Sorry, I'm having some serious software. Let's just try to get back here to whoever was just talking, you're a nice young lady, the domain for sine should be the range for arcsine. Okay, so this domain, can you see my screen now, or do I need to do a share screen?
Yeah, I can see it.
We can see it.
Can you see it okay? Okay.
Yeah.
So a nice young person asking me the question, I didn't give the same, my dear. Please note that the domain for arcsine is the same as the range for sine. They swap. They swap.
I see it. I see it now.
Okay? And then the domain for your sine function is the range for arcsine. Do you see the difference?
Yeah, I see the difference.
Okay.
I just got confused because you know how it says y equals sine x? I still thought about the sine x, like the whole full-on graph. But
yeah, well, we kind of decided we're going to chop him up, didn't we?
I understand. Thank you.
Yeah, we're going to restrict his domain so he can pass the horizontal line test and have an inverse to go with it. So our cos, we restrict the domain in a different way, which means this range over here is that. And then this range is the same as our cos's domain. And so his picture is kind of cute. It looks like, I never memorize it, but it's kind of weird. But I think you, yeah. Okay, now to tangent. If you look at the regular function, he has a lot of vertical asymptotes at all the odd poles of pi half, and he looks like a bunch of these puppies, you know? Obviously does not pass the horizontal line test. Not one-to-one, doesn't have an inverse. Sorry, dude, you failed the test. So what we're going to do is we're going to chop him. Boy, that's really terrible. Sorry, we're going to chop him so that he's only going to have one of these branches, and we're going to restrict his domain to, and we can't do, we're going to have to do parentheses, not brackets, because negative pi halves and positive pi halves, tangent is undefined. So these are parentheses, and the range is negative infinity to positive infinity. So arctan can be happy, and he's got two horizontal asymptotes, one of them located at y equals positive pi halves and the other at y equals negative pi halves. And he looks like, my pen is shot, he looks like that. His domain is all reals, and his range only lies between negative pi halves and positive pi halves. Actually, yeah, okay? So you have similar relationships for arc, seek, arc, cosec, arc, tangent. Go read the book, I don't care, okay? I really don't. Now let's do some stuff that you should have done in a trig class. And if you didn't, I'm just going to say I apologize on behalf of Southwestern College. You got gypped. Go to admissions and records and get a refund. I'm joking. Okay, so if you remember from trig, SOHCAHTOA. So I want you to be able to do all these without a calculator. And certainly if you have your graphing calculator with you, you can definitely go into degrees mode and do arcsine, arctan, arccos, and get some of these answers. But you have to be careful because some of the answers may not be what you think. Why not? Because of these restricted ranges of these actual inverse functions. So keep your eyeballs on those because that's where it's going to hurt you. And by the way, we're going to do some true falses to end today's lecture. And there's going to be some true falses on your quiz on Sunday because I'll open it up Sunday to Monday. And you have to write down the answer and actually on your uploaded work, after you answer true or false with my math lab, you have to give me a full-on reason why. Otherwise, no credit. So it's not that hard. So how do you get this without a calculator? What is this saying in English? In English, this is asking for the angle whose sine value is the square halves. But when they say an angle, not an angle. It has to be an angle that lies range of the sine function. So it has to be somewhere in between negative pi halves and positive pi halves. That's one of those angles. Okay, so if you forgot all of your holy crap, over here to that fabulous unit trig circle that I supplied for you. See that right there? Can you tell me, are there any sine value negative square root of 3 halves that lives, oh my internet, no internet, please don't fail me now, goes from here to in this vicinity?
5 pi over 3.
Well, I like to say you're right, but there's a little bit of a problem. Is 5 pi thirds in the interval between negative pi halves and positive pi halves? Be careful when you answer that. As a number. Like if you had a number line here, here's the x-axis, you know, here's 0, here's negative pi halves, here's positive pi halves. Isn't 5 pi thirds somewhere the heck way over here?
Yeah.
Yeah.
So I need a number that lives in between these two numbers. So here's a tip. Give me an angle that also is the same as 5 pi thirds. In other words, it's coterminal with 5 pi thirds that lives between negative pi halves and positive pi halves on the number line.
So it would be like pi, negative pi over 3.
Perfect. You just won the Bendix washer dryer. Negative pi thirds is correct. Yep. How about arctan of 1? So this is the angle whose tangent, is your screen bugging out like mine is?
Yeah.
Is 1, like it disappeared for some reason. I have no idea what's going on. I've never had this happen to me before. Wow. Okay, so I'll just recreate it. What's arctan of 1? Okay. If you don't know, then you're like, okay, I don't remember. What the heck? So what you're going to have to do is, you know, you could just punch it up on your, that'll work. But does anybody know an angle whose tangent is 1? And what that would mean, since tangent is sine over cos, it would mean both sine and cosine have the same values, since tangent is the quotient of sine over cosine. So if you look down here on your unit circle, if you'll notice that, do you notice that pi fourths has the sine and the cosine is the same value? So that's where, that's going to give us an angle whose tangent is 1. So what angle is that?
Pi fourths.
45 degrees, correct. I'm going to put pi fourths. Why? Why is pi fourths the correct answer, but 45 degrees is going to be wrong?
It's in radian.
Yeah, when I define these functions and their ranges and all this other good stuff, all of these ranges are in radians. So it's going to be illegal for you to give answers that are degrees. Well, my trig teacher let me. Okay, but your trig teacher never officially defined these inverse trig functions like we are finally doing right now. So the legit way to answer, unless somebody gives you permission otherwise, and there are going to be times where I'll let you get away with degrees, but not now. Okay, so the answer will be pi fourths. Okay, let's go a little bit quicker now because I want to get through some of these. Okay, cos inverse of negative square root of 2 over 2. You go look at your unit trig circle. What is an angle whose cosine value is a negative square root of 2 over 2, where the angle lives in this interval, 0 to pi, because our cos, the function has the interval 0 to pi as the range.
Pi over 4? Can you hear me?
Yeah, but that doesn't have a negative. Pi fourths has a positive cosine value, doesn't it?
3 pi
Check
over
the
4?
unit trig circle.
Can
Can we see a circle?
You may. So we want a negative square root of 2 over 2 cosine.
Negative
3
pi over
pi
4
over
or negative 3 pi
No,
over 4?
negative pi fourths, hold on. Negative pi fourths doesn't live in the range of arc cos. The range of arc cos is 0 to pi now. It has a different range than arc sine. It has to live from here to here, 0 to pi. That's our cos's range. So I claim it's going to be 3 pi fourths because 3 pi fourths lives in the range of arc cos, and the cosine is a negative square root of 2 over 2. Now, I know a lot of you hate trig, and some of you are going to go, I'm going to suck at this section because I suck at trig. And my answer to you is, you got time to start reviewing. Because if you hate trig that much, there's going to be some problems in the class. Okay, let's do letter D. Now, when you took trig, when they did any of these arc sines or arc cos or whatever, they probably were pretty loosey-goosey about the answers. And now I'm not going to be loosey-goosey because we officially defined the range. So if you're taking sine of 7 pi 6, and then you're going to take arc sine of that, is that question mark going to equal 7 pi 6? Yes or no?
Yes?
No.
No.
False.
No.
Why? Because arc sine, the range has to be between negative pi halves and positive pi halves. And 7 pi 6 is not a number that lies between the numbers negative pi halves and positive pi halves. So this is not going to be 7 pi 6. Well, then what's the answer? Well, if you go back to your circle, try to pick an angle that lives between negative pi halves and positive pi halves that has the same sine value that 7 pi 6 does. Oh, really? Oh, really? Yeah, I'm not lying. Okay, you'll notice that 7 pi 6 is over here, and the sine value is negative a half, right? Are there any sine values in between negative pi halves and positive pi halves over here on the right-hand side of the circle, but who also has a sine value of negative a half? And I claim it's this guy
11 pi f
here.
over 6.
But hold on a minute, 11 pi 6 is also not a number that lives between negative pi halves and positive pi halves. So what's a coterminal
Negative
angle?
pi over 6.
Negative pi 6. Thank you. Uh-huh. Yes, indeedy. And that's the answer. Okay? Now let's get tough. Well, I thought those were tough. Oh, no, those were the easy problems. Here's where it gets harder. This is, we're going to take tangent of arc sine 4/5. But here, I'm not asking for an angle, even though it sounds like I am. Watch how I do this. And yes, this is going to be on quizzes and exams, like for realsies. So first, look at this and you go, oh my God, what is an angle whose sine value is 4/5? Actually, don't answer that. Well, what do you mean? You know that sine has a value of opposite over hypotenuse, right? So what we're saying is that this angle theta, which I actually don't care what the hell he is, I really don't. All I know is that the opposite side length is 4 units long, and the hypotenuse of this right triangle is 5 units long. And they're just asking for tangent. And hopefully you guys remember that tangent is opposite over adjacent. Do you remember that from trig? Good news,
Yeah.
I do have what the opposite angle is, so half of my answer is going to be 4. The other half is divided by question mark. That's what you have to figure out. But this is a baby algebra problem. Really? Well, the adjacent side length is right here, and you remember from your days of Pythagorean theorem, I'll just call it x, you know that x squared plus 4 squared is equal to 5 squared, right? So in other words, x squared is 5 squared minus 4 squared. In other words, x is the square root of 25 minus 16, which is 3.
3.
Final answer, the tangent of this angle is opposite over adjacent, which is 4/3, and we're done. How about cos arctan of x? It's very similar to that one, but you have to turn this into a quotient. And then tangent is opposite over adjacent. So when I draw a right triangle that goes with this problem, and I always do, and I'm going to ask you to also, otherwise I won't give you full credit. The opposite is an x units long, and the adjacent is 1 unit long. And cosine, I know cosine of this angle has to be adjacent over hypotenuse. Good news, I have half the answer. I already know what the adjacent side length is. Fabulous. What's this hypotenuse? Well, are you able to find the length of this hypotenuse if you're given the lengths of the other legs? Sure you are. This hypotenuse is going to be the square root of the sum of the squares of the legs. Yes? Hello?
Yep.
Yes.
Final answer? Final answer? 1 over the square root of x squared plus 1. Okay, I'm going to do a hard one. This is a challenge. Because, first of all, sec inverse is not a button on your calculator. If that said cos inverse of negative square root of 2, I could just get myself into, you know, degrees mode and do a cos inverse and figure it out. There's no sec inverse button on my calculator, so that's a problem. So what am I going to need to do? I need to think. I know that secant, this is basically the angle whose secant value is negative square root of 2, which I'm going to turn into a quotient. Because if you remember, secant is just the reciprocal of cos, which means that's the adjacent side length and that's the hypotenuse. And I never like my hypotenuses to be negative, so I'm going to put my adjacent to be negative. And you're probably thinking, yeah, but if we're going to be talking about a triangle, you better not have negative lengths. You're right. But what I'm going to do to overcome that is I'm going to draw the -1 sort of in the negative x direction. So there's my adjacent side length. There's my theta. And my hypotenuse is square root of 2. So I'm going in the negative direction there. Okay? You with me so far?
Yep.
So what is this angle? They're actually asking for the actual angle now. It's like, oh man. Well, one thing I know is, since on my calculator I do have a cos inverse button, what would the cosine be? Well, the cosine is adjacent over hypotenuse, and we already have both of those in hand. It's -1 over square root of 2. So really what we want is what's cos inverse of -1 over square root of 2. And you can use your calculator. Here's the tip. I'm going to rationalize this denominator if you don't mind. And then I'm going to look at my diagram of the unit trig circle and try to figure out what the angle is. So look at the diagram. It's a hot mess, I know. But since arc cos has the range between 0 and pi, are there any angles between 0 and pi whose cosine is negative square root of 2 over 2? Do you see any
35.
choices here?
3 pi over 4.
Very good. Bingo, dingo. You get what's behind door number. Three pi fourths. Okay, we're done with that page. I know that was like killer, but if you got through it, congratulations, and go do some homework problems because I put a whole bunch of homework problems that have the same flavors. Go watch the view and example and so on, okay? Let's get into calculus, finally.
Just quick question. The limit, you get it from the range set, right?
The limits for the range are what?
The limit, like when you say, well, you cannot go from 0 to pi, you get it from the range set, right? From the previous problem that we did.
Well, what I want you to get it from, my dear, is this first page. When we did all these graphs and we denoted what are the ranges for each of these inverse trig functions.
Uh-huh.
So for arc sine, it better be, you know, the angle better be a number between negative pi halves and positive pi halves.
Okay.
For arc cos, you're restricted to 0 to pi.
Okay.
For arc tan, it has to be between negative pi halves and positive pi halves.
Okay, I got it. Thank you.
Okay, that's where we're getting it from. It's not that I'm like just deciding off the top of my head, yeah, it's got to be between 0 and pi just because I felt like it right at this moment. You know, no.
I'm sorry. Yes.
It's defined like in advance for all time. Right here was the key page for all of the intervals that are legit or not.
Thank you.
You're welcome. All right, so going back to this business, let's get some derivatives. Now, you know, I'm kind of running short on time, so I'm only going to do one of these derivations, if you don't mind. I'm going to skip this one. For those of you that really, really want to see it, I'll do it for you in office hours. It is pretty cool, and you can probably find it online. Let's just do one of them, because, you know, it's similar. So how do I take the derivative of arc sine? I mean, holy crap. I don't know. We didn't learn that in Calc 1 or anything like that. I know, they didn't teach it to you. All they taught you is how to take the derivative of sine. So we're going to actually use your knowledge from Calc 1 to help us do this problem, as well as a trig identity. Okay, really? So what I want you to remember is two things. So two facts will help us do this problem. First, if you had a function f of x is equal to sine of x, what is the derivative of sine of x? Somebody tell me.
Cosine x.
Cosine x. Good. So that's one fact. Another fact, actually we might need three facts. So there's one. Here's a second one. Hey, do you remember sine squared plus cosine squared is equal to a really nice number?
Pythagorean identity?
Yes, so sine squared x plus cos squared x is equal to?
1.
1.
Yay! Yep. And then one other thing that you're going to get really unhappy with me about, and I apologize in advance. Do you remember implicit differentiation from your Calculus 1 days?
Yeah.
Yeah, and what you did is you used the chain rule. So anytime you took a derivative of something that had the y in it, where y is a function of x, you had to use the chain rule and drill a little deeper. So all three of these are going to come help me derive the formula for the derivative of arc sine. Now, folks, I'm not going to ask you to derive this on any quiz or exam for your future. However, if you're a math major, let me just warn you in advance. When you take higher levels of math, all you do is proofs. That's all the upper level math is. So if you don't like proofs, major in engineering instead. If you like solving problems and you're good at math, major in engineering. Plus you have a better shot at getting a job as an engineering major. Math majors have a tough time getting jobs. Let's do the derivative. So what we're going to do is, first of all, this function I don't know how to do. Can't get the derivative. So what I'm going to do instead is I'm going to take sine of both sides of this equation. Why am I doing that? Just stay with me. This is a cool proof. So on the right-hand side, you're going to use your knowledge of inverse functions. Sine of arc sine of x is just going to boil down to x. So x is equal to sine y, okay? And so now what we're going to do is we're going to work with this equation, and we're going to use implicit differentiation, which is a Calc 1 technique, to get dy dx. So let's see if you can follow this and you remember any of your Calc 1 material. Let's do the right hand. So what you're going to do is you're going to take d dx of both sides of this equation. Keeping in mind that anytime we differentiate with respect to x of the y, you're going to have to use a chain rule. Let's do the right-hand side first because it's easy. Everybody in the room should know. What's the derivative of x with respect to x? I'll check the chat. Everybody in the room had better get this, otherwise I'm going to have to kick you out of my class.
It's 1.
Thank you. It's 1. Oh, good. That side is just a 1. Fine. What about the right-hand side? Uh-oh. Well, when we differentiate sine of y with respect to x, using the chain rule, we first differentiate sine, which is cos, so cos of y, times the derivative of y with respect to x. Well, that's dy dx. And now solve this equation for dy dx. Well, that's easy. I'll just divide both sides by cosine of y. That's correct. And we're almost done. This is the answer, except we want our answer to only have x's in it. Really? So yeah, we're going to use the trig identity. This trig identity, if you solve it for cos, your cos will be the square root of 1 minus sine squared. So when I replace this cosine of y with the trig identity, 1 minus sine squared of y, like that, and then we're going to do one more trick, one last substitution. What did we start out with at the very beginning of this derivation? What is sine y the same as? Hello?
X.
X. So I'm going to replace the sine y with x. Moral of story, the derivative of arc sine of x is 1 divided by the square root of 1 minus x squared. And I'm done with the derivation. Congratulations. You've now just seen a derivative for one of these weird inverse trig functions. Yay! Success. So here is the chain rule version for all 6 inverse trig functions. And now you're thinking, oh my God, there's so much to memorize. I want you to notice they come in pairs, so you don't have a lot to memorize. Focus your eyeballs on the first row. And notice when you take the derivative of arc sine of u, you're going to have that square root of 1 minus u squared, which is similar to my square root of 1 minus x squared. And then using the chain rule, you'll have your u prime. You know, if u is something other than x, it'll be something other than 1. But the derivative of arc cos, doesn't it look at almost exactly the same as the derivative of arc sine? With one slight difference. What's the difference? Can anybody see it?
The negative?
Exactly right. This just has a negative. Everything else is the sine. Very good. So there really isn't much extra to memorize. You just have to remember, oh, arc cos's derivative is the opposite in sign of the arc sine's derivative. Success. Similarly, if you focus your eyeballs on the second row, another thing becomes apparent. The derivative of arc tan does not have a radical in it. It's going to be u prime all over 1 plus u squared. And then the arc cotangent is exactly the same, except it has the minus sign. When you're taking the derivative of arc secant, it's hellacious. You're going to have u prime divided by absolute value of u times square root of u squared minus 1. Notice that these radicals are not the same. A lot of students think they look exactly alike. No, the arc sine has 1 minus u squared, and subtraction, the order matters. The arc secant has it backwards, has it u squared minus 1. So please don't mess this up. Use your formulas correctly. And then arc cosecant is the same as arc secant's derivative. It just has a minus sign. Okay? Now I want to say something about Briggs. I haven't said this yet, but I'm gonna. Full disclosure, Briggs is a crappy textbook. Briggs sucks. I hate it personally, and the more I have to work with it, the more I hate it. Well, why are we using it at Southwestern? Good question. Because my math lab is so good. Otherwise, we would not be using this book. It's horrible. So let me tell you one horrible thing about this book. When you open up the book and you read this section, all of the formulas they give you in the book all only have x's in it. They don't have the chain rule version. Or see how I'm doing arc sine of u? And so you're going to have to use the chain rule and have that u prime factor in there. Briggs doesn't give you the train rule version of it when they give you all the formulas, which is really crappy because they expect you to get it. They give you a lot of homework where you're expected to know the chain rule version. Oh, thanks, guys. But they never give me the actual formulas with the chain rule. So you're welcome. This course reader is worth its weight in gold, people. That's what I'm trying to tell you. Okay, so now let's do some problems. Okay, are you ready? I'm just going to do a whole truckload of problems, and I might even ask you to try one or two, or give you one or two, okay? Just for kicks and giggles, I'll think of one. Okay, we're going to start off easy, but the whole idea is you're going to use these formulas and just plug and chug. You have to identify the u, and then you identify the u prime, and then make all the correct substitutions. You might have to do a little bit of simplifying and reducing and cleanup to make it look nice, but other than that, it's just plug and chug. Okay, here we go. There's a function, find the derivative. Well, it's an arctan function. Yeah, I know. So, you don't have this memorized yet. Go look at the formula sheet. What is the derivative of arctan? Well, the derivative of arctan of u is u prime divided by 1 plus u squared. Easy peasy. And this 4 is just a multiple, so we better write it down. So, who's the u for us? Tell me. I'll check the chat. What is it?
2t. 2t.
Very good. So then what is u prime?
2.
Very good. So after doing some substitutions into this cute little arctan formula and then do some cleanup, 4 times 2 is 8. And then down here you want to use your exponent laws. There's your derivative right there. And we're done. It's that easy. Or is it always that easy? Sometimes I like you to do a lot of algebra. So now let's do one that's a little tougher. So this one is going to involve algebra challenge, number 2. Okay, why? Well, you'll see in a moment. First up, I need to take a derivative of arc sine. I don't have that memorized. Let's look at the formula. The formula says if I'm going to take a derivative of arc sine, I'm going to have u prime in the numerator and a square root down in the denominator, square root of 1 minus u squared. So p prime, the 16 is just a multiple. I'm going to have u prime all over square root of 1 minus u squared. My u is x over 4. What is u prime?
We gotta do the quotient rule with this.
No, I'll give you a hint. X over 4
1 over 4.
is the same as 1/4 times x. Does that make it easier to take the derivative? What's the derivative of
1 over 4.
1/4 times x?
1/4.
1/4. No quotient rule needed. Now you could use the quotient rule, but that would be overkill. That's like taking out a shotgun when all you needed was a little BB gun. Okay? It'll still get you the right place, but don't do that unless you have to. Okay, so now plug in your stuff. So I still have my 16 times my u prime, that's 1/4, all over the square root of 1 minus the u getting squared. But u is x over 4. Now, if you put that somewhere on your paper, I will give you 1 point out of 10. That's it. Congratulations, you plugged in crap in the right spots. Yay, good for you. But I won't give you full credit. Why not? It's right, because you need to clean it up. It's ugly right now. I want full cleanup. So hopefully the obvious cleanup is just the numerator is just going to be 4 after reducing. But your denominator is pretty gross because I don't like it when you have a fraction inside of a fraction. That's considered a complex fraction. Well, what do you mean? How am I going to clean this up? Let's do some scratch work. So I'm going to look at the radicand. The radicand is the junk underneath the radical. Let's try to rewrite it as a single quotient. This is just algebra, but you have to be good at algebra if you're going to be good at calculus. And if you haven't figured that out already, I don't know how you pass Calc 1. When I teach Calc 1, on day 1, I announce to the class, those of you that are strong in algebra, calculus is going to be easier than algebra. Those of you that suck at algebra, you're going to hate calculus. Because if you have weak algebra skills, your calculus is very painful. Okay, So how do we rewrite this as a single quotient? If I give the 1 a denominator, what's the LCD of these
16.
fractions?
16.
16. So if I multiply the top and bottom of the first term by 16 over 16 there, and now I have like denominators, which means I can combine them into one big old fraction. Is everybody with me so far?
Yes.
Okay, now what? I'm done with my scratch. What I'm going to do is I'm going to replace what's underneath that radical with this big old yucky thing. Now you may be thinking, no, that looks worse than the original. And I'm going to say, you're right, but hold off a minute. I'm going to use a rule of radicals that allows me to rewrite that radical of a quotient as the quotient of radicals. And I'm almost done, because square root of 16 is 4. And now I'm going to, this still is ugly because you still have a fraction inside of a fraction. I'm going to turn it into a multiply problem. I'm going to multiply the numerator by the reciprocal of the denominator. You guys have seen that in arithmetic class, right? And my final answer, and I know this took a while, is that. My final answer is 16 all over the square root of 16 minus x squared. That's as simplified as it gets. Questions? Let me ask you a question. Is this true or false?
False.
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 Good. That is false. If I see anybody in the class doing any of that nonsense, you're going to hear from me. You're not allowed to distribute a radical over a sum or a difference. That's illegal math. It's not even close to being true. Okay? So please don't do it. You know, especially because I see people who get the right answer and then they'll go an extra step and then I have to take away all their points. It's terrible. Okay, so that was an exercise in futility. And now let's do another one, problem 3. So what about problem 3? What makes that one like amazing? What's the big deal? Well, look at the first term. What rule that you learned in Calc 1 are you going to have to apply to just that first term? Product rule. And you're going to need to know how to do the derivative of arc cos. That's a double whammy. And then there's a triple part of the whammy here, is this part is easy because you learned how to do this in Calc 1. And you're going to use the chain rule on that because you're going to rewrite the square root using exponents, and then you can use your power law for derivatives and the chain rule and go ahead and take the derivative of that. So here we go. The f prime is going to be, when I use the product rule here, you're going to take the derivative of 2x, which is 2, multiply that by arc cos, plus the derivative of arc cos, which is negative 1 over the square root of 1 minus x squared. And then you're going to multiply that by 2x. And then minus, and then you're going to differentiate this beast. The 2 is just a multiple. The 1/2 will come out in front. And then you're going to have, let me get rid of this. Sorry. You're going to have 1 minus x squared raised to the 1/2 take away 1 power. We'll figure that out in a second. And then times, using the chain rule, what's the derivative of the inside of the parentheses there, that inside layer of 1 minus x squared?
Negative 2x.
Very good. And then clean this mess up. I don't like negative exponents, so I want all the cleanup happening here. So I still have 2 arc cos x. This beast you can kind of combine and put the minus 2x up there. Okay. And then this reduces to 1. And then this is going to be the numerator. And then this 1/2 minus 1 is really negative 1/2. So when I rewrite it using positive exponents only, I put it in the denominator and change the sign. Now this minus and this minus together make a plus. Does anybody see anything happening with these two terms?
They're the same.
They cancel each other. You see we have the opposite of this and then we add it to the positive, yeah, these add to 0. Final answer, 2 arc cos x. Does that always happen? No, but I just put that problem on my lecture notes because I thought it was sweet. Because it can happen. Okay, so this is the answer to 3. I didn't give myself enough room, obviously. Let's do 4 right now. Do I need to use the product rule on number 4, yes or no?
No.
No, because it's a function.
No, it's a function of, so no, I don't. No, we don't. I'm going to shut up for a few minutes, and I want you to work on this one with a buddy. I'm serious. I'm going to put you in breakout rooms right now. We have 41 people in the room. I'm going to create, hell. How about, you're going to get invited to join a breakout room. Please go in there now. Go work on the problem. Hosan, Artelani, are you still in the large room? You need to join breakout room 1. Kobe, are you there? Okay, let's just see here.